Okay, this lecture we will discuss one of the most important aspects of our understanding of the universe, in fact. Momentum is a quantity that we're going to define and utilize quite a bit in this class. So today we're going to understand where it comes from and how we use it. So briefly, momentum is a quantity that we will learn has a special place in our understanding of the universe itself. The reason I say that is because within the universe there are certain things that you can neither create nor destroy. And for the universe, that means that the amount that was there in the beginning of time is the amount that's there right now and will be that constant conserved quantity forever. And that's a pretty bold statement. Momentum is a conserved quantity. The amount that we have now is the amount that we have forever. You can never create it, never destroy it. That's a pretty bold statement. But it's a fairly simple thing to define. We give it the letter P. It's called momentum, but we give it P. P is, I'm going to say, approximately equal to mass times velocity. This is mass. This is velocity. So as defined, momentum is a vector quantity. It's a scaled version, scaled velocity. Now, I say scaled, but it's an important scalar. Mass is a positive quantity. That means that momentum always follows the direction of the velocity. So if you know the direction of the velocity, you know immediately the direction of the momentum because the mass will always be a positive scalar quantity multiplying the velocity itself. So this is important. Now we can rewrite Newton's laws in terms of momentum. And what I will say is that it simplifies our understanding and now relates momentum to forces. And this is what we need to keep in mind. So I will say the momentum of a body could be any sort of body, from a molecule to a planet, remains constant unless the body is acted on by an outside force. That is Newton's first law in terms of, so I'll call this N first. Newton's first. Okay. Like any vector, momentum can change. It can change its magnitude and it can change its direction. So I will represent P as being the magnitude of P times the direction of P. Either one of these quantities can change. Either one. So that means that I can think about the trajectory of a physical thing now. So, for example, if I have the ocean and a fish decides to jump from the ocean and follow some trajectory, so that fish will have a momentum given by its mass and its velocity. And it will, I will say this is point A, this is point B, and this is point C. And so the momentum at point B, these are vectors, and point C will be quantities that we can measure. And I can say that the delta P for my fish, delta P for the fish, is going to be PC minus PB. And as such, this is my final, this is my initial. So let's look graphically at what that might look like. So here's my PC, and here's my PB, and here's delta P. Okay? Right. So, changes in momentum can come with directional changes, but they can also come with magnitude changes. So I would say that this fish, the magnitude, for example, of PB, in this case, might be equal to the magnitude of PC. But the direction of those two vectors, P hat B, is not equal to P hat C. I put a hat on here accidentally. Okay, so that's change in momentum. There's another type of change in momentum, of course, and that is if something speeds up in a direction. So what we know from this example is that the fish experienced a force. It had to. Newton said so. So, what's another way of thinking about change in momentum? Well, I could imagine, for example, a ball hitting a wall and rebounding off of that wall and ending up at some point, and I'm going to just translate my ball down a little bit so we can keep things clear. Here's my P initial of the ball, and here's my P final of the ball. And in this case, I have changed my momentum. Perhaps, again, the magnitudes may not have changed, but certainly the directions have changed. So what acted on my ball to make it undergo this change? Well, it has to be a force due to the ball and the wall's interaction. And so this gets to a very important concept that we're going to have to work through, and that is the idea of a system and a surroundings. So systems and surroundings are very important things to think about. And so the momentum principle, when we get to that definition, we will have to choose a system and a surrounding. And so for this example, where I have a ball, the ball, and I'm going to just write this down to be very explicit, the system, the thing I'm interested in analyzing, in this case, is the ball. And for all of chapter 2, it will be single objects, single particles, single materials, things that I can identify as being one component. There's lots of little things inside of this ball that makes it up. There's the little furry hairs that are on the outside if it's a tennis ball. There's the rubber, there's all the molecules, but I'm going to lump that all into the thing called the ball. The surroundings that's going to be everything else in the universe. It could be the wall. It could be the earth. It could be the wind. It could be a nuclear blast that happens somewhere off in space. I don't know. It could be every star in the universe. Everything else is the surroundings. The thing we have to keep in mind is that can get a little overwhelming when we try to think about all the interactions between the surroundings and the system. However, we can make some approximations that the moon is probably not exerting a lot of gravity on this ball as it bounces off this wall in this time interval that I've given here. So we don't consider it. We eliminate it as a piece of the surroundings. It's there. We always have it. But in physics, we make approximations sometimes that help us solve problems when those approximations are good to make. And one of those approximations is that the moon is not affecting the dynamics of this ball. Okay, so that's something to consider. Now, I want to take a little bit of a detour just for a little bit of fun, and to help you understand some things about physics, into what I mean by the statement that P is approximately equal to mv. What does this mean? What that means is that some things can actually go very fast. And by very fast, I mean close to the speed limit of the universe. So the speed limit of the universe is the speed of light. So it's c, what we call the speed of light. 3 times 10 to the 8th meters per second. That's c. I'll just call it c. It's not a vector quantity, it's a speed. This is the fastest anything can go inside of a vacuum in space. Light has a limit, and it sets the limit for the rest of the universe. Experimentally, we can show that for speeds much, much less, for velocity magnitudes much, much less than this, that this is almost an exact representation of the physical world. But it is an approximation. As my speed, the magnitude of my velocity, approaches, goes towards c, then all bets are off. I have to change things. And Einstein established that weird things happen. This is called special relativity. Weird things happen when I start to approach the speed of light. In fact, it gets harder and harder to change my momentum as I approach the speed of light. And so the actual statement of the definition of momentum with the real equal sign here is equal to this thing called gamma times m times v. So what is gamma? Gamma, turns out, is a limiting factor. It's a thing that we have to calculate every time we have to calculate the momentum for fast things. So gamma is a scalar quantity, no vector above it, and the magnitude of gamma, what it's equal to, is 1 over 1 minus the ratio of my speed to the speed of light squared. Now, this quantity has some interesting things associated with it, and that is, how does it look graphically? So it looks like a diverging function. Now, what does that mean? It means that it will undergo a large gain in value as my speed approaches the speed of light. In the case where v is very, very small compared to c, then this ratio, v over c quantity squared, if this is 3 times 10 to the 8th meters per second, and let's say a basketball travels 5 meters per second, then this thing very, very quickly approaches 0. Because I'm taking the ratio of a very small number divided by a very big number squared, which is, of course, again, a very, very small number, very close to 0. And so therefore, gamma, for speeds that we know, walking, cars, things like that, that approaches 1. 1 minus 0, square root of 1 is 1. 1 over 1 is 1. So for low speeds, gamma is approximately equal to 1. However, for high speeds, as this ratio gets closer to 1, look what happens. As my speed approaches the speed of light, this ratio becomes 1. 1 squared is 1. 1 minus 1, that's 0. That's kind of weird. So for high speeds, 1 over 0 is a bad number. It's infinity. For physics, it's kind of a bad number. For math, it's okay. But we call this a quantity that diverges. So here's the value of gamma as a function of the ratio of v over c. And I'm going to call this point right here 1. When I reach the speed of light, v over c is 1. So this function looks a lot like this. It's 1 for a lot of values, and then as I approach, it does what's called in mathematics diverges. It goes to infinity, very close to the speed of light. So, well behaved for all of the world that we see every day, but then badly behaved when I approach the speed of light. The reason is because this mass starts to become a problem. If I try and speed up a massive object closer to the speed of light, I run into an issue.